Okay, so let me go ahead and get started. Very good morning, all. Thank you for joining us for this talk today. I'll talk about some of the research that goes on in my group, but many of it is very collaborative in nature with many other faculty at IISc and other institutions as well. So thanks to all of them and to my students. So just as a brief introduction for the Indian Institute of Science, which may not be as popularly known as the IITs and Institute of Technologies. So we are over 100 years old, which is relatively long by Indian standards, not by UK standards. And we were sort of formed as a sort of partnership back then between the royalty, the Mysore Maharajas, and one of the founders of Tata Group. That's fairly popular. And today we are one of the top university in India. We are predominantly a research university, as also a predominantly a postgraduate institution. Most of our students are PhD students and master students. They're a very small graduate population. And we sort of span the disciplines between the sciences and technology. So all the engineering disciplines, including computer science, are reflected, as well as many of the scientific disciplines. And we do have many interdisciplinary programs that we do as well, everything from nanotech to brain and AI to robotics and quantum and so on. And we do have a medical school that's coming up in the next couple of years. The department I'm part of is the Computational Data Sciences Department, which itself is an interdisciplinary department. So we also have a traditional computer science department separate from this. In my department, we have about 20 faculty. It's a fairly modest-sized department and about 100+ students, most of them PhDs. And we work at the intersection of applications, systems, and methods. Right? These could be both computational and data science methods. Systems could be anywhere from the distributed systems I'll talk about today to even HPC and supplementing systems, as well as diverse applications. Right? So half the faculty in our department are from the computer science background, but the other half are from various engineering and scientific backgrounds. But they all tend to use large-scale systems. Right? That's one of the common threads across us. The group I lead is called the DREAM Lab, Distributed Research on Emerging Applications in Machine. And we sit between the hardware at the bottom, which keeps evolving over time. So we're dealing with cloud and edge computing, which is a theme for today. But it grows over time. It could be mobile devices. We are also working with drones, which are simply another form of mobile computing. You might have quantum that's around the horizon, commodity hardware, containers. So the hardware ecosystem is going to evolve with wherever the industry is going to take us. Right? As academics, we don't have a very big role to play in adoption of hardware. It's there, and we have to use it effectively. Right? And similarly, at the top, from the application space, that again is evolving. Right? In the last 5-10 years, machine learning has really permeated across all domains. So that itself becomes a very key thread that ties various disciplines. But we work a lot with smart cities, which I'll talk about in this, as well as things like fintech and drones and so on. Right? But our research stands in the middle, right, between the hardware and the applications. How can you make these hardwares more accessible to all these emerging applications? And this is in two parts. So one, how can you make these hardware platforms programmable, right? So if I have an application, how can I come and map it in an intuitive way, in a way that will run on this hardware platform? This could be anything from things like federated learning, which I'll talk about today, to data flows and workflows, to even various types of graph abstractions that we worked on, temporal graph abstractions and so on. Right? So that's where the algorithms and abstractions come into play, including parallelizing or designing distributed algorithms for traditional single machine algorithms. That's one part. The other part of it is how can you take these abstractions and run them effectively through distributed software platforms on such heterogeneous hardware. That's again a key focus for us in terms of enabling various properties of scalability, reliability, efficiency, cost effectiveness, and so on. So that's again another piece that we work on as in our group. Right? So broadly, this is motivated by sort of the evolution in the last 5 to 10 years of various, both in the application side, the hardware side, as well as in the analytics side. Right? So just to give you a sense of this, all of us know that ML is pervasive nowadays. You name it, and every domain is going to try and tap into the power of machine learning and the power of the availability of large-scale data. Right? In fact, to the extent that even some of my computational science colleagues have you do things like physics-inspired neural networks and so on. So where even things like weather forecasting is having elements of ML to help bootstrap some of these large-scale simulation models. Right? And in addition to all the traditional uses of ML in social media and e-commerce and so on. Right? But a key challenge with ML is both on the training side and on the inferencing side, it is computationally intensive, right? And these are some recent stats I pulled out from Hugging Face, which is a very popular repository for hosting ML models. And all of these, since large language models are the flavor of the year, I just picked out some of the large language models, right? These are some of the largest. It goes everywhere from close to 1 trillion parameters. We are approaching several hundred billion parameters in size for the largest ones, right? To things that are tens of billions of parameters in size. And as you can see, pretty much every company out there, every large company is getting into the game, right? Because if you don't sort of catch up, you're going to be left behind and they might become extinct, right? So Apple has their one, Facebook has their one, Microsoft, Google, everyone has their own large language model. And this is effectively an arms race that they're competing with each other, right? And obviously training these models take a lot of computing power, a lot of energy, a lot of money, right? Microsoft apparently spent $1 billion in putting together the first ChatGPT 3 that came out in the public domain. So these are costly from training, right? But again, not everyone has got $1 billion and not everyone needs to train a model from scratch, right? So that doesn't make sense. But that being said, even for those who are training more modest model or retraining models, you do have to invest in a lot of computing power. So even at a smaller scale, it is going to challenge, right? The accelerators that you have, the GPUs that you have, and so on. And if you sort of start shrinking further, this is also going to start challenging your inferencing, right? So to the extent that many of the PC companies have a new market in terms of having AI-enabled PCs. They just pop in a TPU or some kind of a AI accelerator, and they just call it, this is AI-enabled. You have to upgrade your laptop or your PC. Otherwise, you're not going to be able to run your local AI bot on your machine, right? So, which means that accelerators themselves are going to be pervasive, right? So far we thought accelerators are, hey, you need a heavy GPU workstation, special purpose one that you have to buy, and so on. Or if you have a gaming machine, you might have that. But in the next year or two, every PC that's out there is going to have an accelerator, right? At least for inferencing, if not slightly more powerful than that. So that's the one piece of motivation, which we are all familiar with. AI, compute heavy, and we need to sort of, it's everywhere, and we need to start using it. Second part is from the application side of things. And this is the enabling technology for some of the smart cities what I'll talk about is the Internet of Things. Again, this is enabled by affordable sensing and actuation devices. There are estimates of billions or trillions of these IoT devices out there. And they're starting to come on. It may not be the trillion scale, but if you look at the ceiling, you may or may not see about 100 sensors on top of you and actuators, right? So effectively every new building or every new car that comes out has a lot of these sensing capabilities. And communication, we take it for granted, 4G, 5G, 6G down the line, it's all over. And these are all the enabling technologies, right? So the idea of IoT itself is probably 20, 30 years old, but it's all come together now, right? And the ability to observe and collect data, communicate it to the backend, potentially to the cloud, doing analysis on top of that, taking decisions, and communicate it back in a closed loop cycle back to the complex system that you're observing. So these are cyber, physical, and social systems that you're trying to observe and analyze and effect changes to achieve various quality of services and quality of experiences. And compute and analytics is a key piece in all of this. Right? And just to give you a sort of quick flavor of some of these smart city and IoT projects that we have worked with in the recent past and are continuing to work on. So one of these, and again, smart cities is a key challenge in India, being the country with the largest population now, and also rapidly growing urban population, right? So some of the largest cities in the world are in India, right? So by solving challenges in cities, you're having very quick impact on a large population scale, right? Just as a metric, right? The Bangalore city where I'm from has a population of about 14 to 15 million, which is about 2 Londons in a single city, right? And Delhi is about 6 Londons or something like that, right? So one of the challenges that we worked on, and the collaborators at IIT Kanpur and IIT Bombay, is in addressing air pollution, right? Delhi, the capital of India, ignominiously is the most polluted, has the most polluted air in the world, right? So that's a big challenge that we've been working with some of our colleagues at IIT Kanpur to address. And one of those is to get, how do you get the data to even understand how much pollution is there, right? And to that end, typically what ends up happening is that you have these pollution monitors that are set up. The one that you see in the middle over here are very costly equipment. These cost a couple of $100,000 to install, and you might have maybe a dozen in a large city because that's all you can afford. But that's obviously insufficient from a spatial scale perspective, because a lot of pollution happens through in micro regions, right? So if there's a traffic junction, that might have a certain type of contribution to the pollution. If you've got construction going on, that's contributing. Just having 10 or 15 sensors in a massive city is inadequate from even understanding where pollution is coming from, let alone intervening. Right? So we worked with our colleagues on deploying low-cost air pollution monitors, which are 1,000 times cheaper than the costly ones, which means you can afford to have 1,000 of these, where you could instead of one costly one. So, so those are the ones that you see at the bottom right of your screen, which are this is part of the Saturn project. It's an Indo-US project that this is funded through. So this sort of gives a scale, but again, there's no free lunch. And one of the challenges with these low-cost sensors is that they are not as accurate, right? Put it another way, their calibration is off, right? So you're not going to get 99.9% accuracy that you might get with these gold standard scientific devices, but it's going to be worse. So the question is how worse and how acceptable is that? And what you see in the plot over here is looking at the yellow one is the reference grade ground truth data. And the A1 that you see is what these sensors report out of the box. Right? As you can see, the orange and the yellow are fairly far apart, right? So sometimes even 2x off, right? So it's almost, it's got a broad trend, but it's very noisy. So what we did, and without sort of getting into too much detail, even by using very simple machine learning modes, I wouldn't even call them, these are just regression-based modes, as simple as they get. What we are able to do, this blue and the green that you see, are how we are able to use calibration data to actually correct for some of these deviations and able to get somewhat within 90% accuracy, right, of what the ground truth data is, right? So, so sort of, I like to joke that this regression model is worth $100,000, right? And it's probably three or 6 months of data collection and a couple of months of analysis, and you're able to get that. But again, there are challenges with these. So there's a more complex paper where our ML colleagues put in more sophisticated models to look at robustness across time and across regions and so on. But point being, this is an example of how ML can help address some of these challenges. And again, as part of a broader IoT deployment out in the field, right? We also have done work with water distribution networks within the Bangalore city. The earlier one was deployed in both in Delhi, Bombay, and to some extent in Bangalore. This one is with the Bangalore city in terms of water distribution. And here we were looking at how can you deploy water quality sensors to detect contaminations, right? In a city of 14 million population, right? And the idea is that if, let's say, some pollutant seeps into the water network, or even if there's a active threat by someone intentionally doing this and so on, or if there's a leakage and such, how quickly can you detect it and can you warn people in the city? And this is actually an actively studied area. In fact, some of the earliest such results came out of even the Homeland Security in the US, where they actually had challenges where can you come up with algorithms to detect terrorists introducing sort of pollutants into a water network in the US and so on. So there are some sort of state-of-the-art techniques out there. There was part from the EPA being one of them. But we were able to develop certain graph-based algorithms, temporal graph-based algorithms, to help do a trade-off between how many sensors do you need and how quickly can you get coverage. Right? And what you see over here are the light blue are the ones that we developed as part of this Equator project with the Bangalore city in terms of time to detection, which is comparable with the state of the art, which is TerraSpot. But also we are able to do better in terms of how many people are affected, right, before you detect the pollutant, right? There are multiple metrics. And in this particular metric, you're actually outperforming some of the state-of-the-art techniques, right? So again, this is and the other benefit of this is that you need very limited field data in order to incorporate this. And of course, this is also optimized for some unique characteristics within India where you don't get 24/7 water supply, right? So over here, most of the developing world, you open the tap, you expect water to come immediately. So in India, you need to have these overhead tanks because you get water supply maybe 6 hours of the day, and you need to fill up your tank, right? And for the rest of the day, you're actually supplied from the overhead tank, right? So if you run out of water in the tank, you're out of luck, right? You have to wait till the next day, right? So how can you even take into account this intermittent supply, right? Because the water network itself is not steady, right? If the supply is variable, how can you take that into account in designing these sensor deployment algorithms? Was one of the novelties in our work. Another work is more recent in terms looking at how do you do demand prediction within microgrids in a privacy respecting manner. Right? So here the use cases could be everything from campuses like IISc or Cardiff, where you might want to understand what's the power usage at different buildings or units, to even software technology parks, where you might have a closed campus, you might have 20, 30 large technology companies in that software park. And these are very, very tech heavy, meaning you might have solar panels, you have EV charging, and you have, in addition to power consumption. And in such scenarios, the ability to observe your power usage becomes sensitive information, right? So if I am doing a product launch in the next 1 month, right, and my competitor shouldn't know when that's happening, right? Just by observing the power usage of a company, I can figure out how many people are working late, right? Is there a surge in the computing usage just by observing power, right? And I might be able to do some predictions, which is something I might not want to reveal, right? So here we are looking at how can you avoid sharing your power usage data with any central entity, but have a central entity, because the central entity for the software park has to make decisions in terms of power purchases from external sources, how much they might want to have predictions of solar power supply, EV sort of charging, as well as predictions of how the different companies are going to be using power, so that they can manage their power purchase agreements and so on. So we have sort of developed or applied some of our federated learning frameworks, which I'll talk about in more detail later, to do such demand prediction, right, within microgrids for various entities, without those entities actually sharing their raw power consumption data, right? And that was done with Accenture. And one of the big projects that we are currently working on is in terms of how can you bring all these ideas together as part of a smart city stack, right? And this is a reference diagram from the Government of India, the Ministry of Urban Development, where they've sort of put this as sort of where they want all cities to go towards, right? Starting from the core services of sort of data repositories that you maintain and manage, to applications that come from top, both user-facing applications and policy applications. Right? In fact, IISc owns one of these pieces. In the last 5 years, we have developed something called IUDX, which is a default data exchange platform for smart cities in India. And it's deployed in about 60 cities across the country. But this primarily looks at just collecting data, aggregating data, and making it available through a standard interface, right? Through various end user applications. What's missing from this piece, and we are working on currently, is this analytics piece, right? How can you provide some standard analytics services on top of this data, so that you can come in and an application can sort of quickly pick from an existing analytic from a suite of it and rapidly compose new applications that are available, right? And taking this one step further, it's about developing digital twins for the city. Again, that's an ambitious goal. The word is bandied around very easily, but developing something that can look at different domains in an integrated fashion is a challenge that we are hoping to address as part of this project. Right? And to that end, mobility is one of the key questions that we are trying to answer. And this is an example of a proof of concept we are currently working on. This is in the neighborhood of IISc, where we're trying to understand what are the counts of vehicles that are going across this particular junction, right? Because if you look at sensors that are available within the city for traffic monitoring, only thing that we have access to is video data, right? So there are traffic cameras for detecting violations, and there are also sort of safety cameras around the city for understanding the sort of safety and security of people in the city, right? So we have about 6,000 to 7,000 cameras deployed around Bangalore. And we've been looking at, and so far the data has been primarily used just after the fact, right? If someone reports a theft, maybe they go on and scan through that particular video camera, or if there's some automated challan or ticketing that happens for some violations and so on. But what we are trying to do is, can you make use of all this data in a fully automated manner by throwing in a lot of these computer vision-based algorithms? And one example over here is, can we use this for counting the number of traffics that are flowing in different directions, right? And this is just a very, very early prototype, but the idea is to try and get a mix of vehicles. As you can see, you've got auto rickshaws, you've got two-wheelers, you've got cars, you've got buses. Can you actually get a mix of the types of vehicles and the velocity of vehicles and so on for different roads for which you have this camera data, and try to build essentially a temporal graph, right? So someone like Google, for example, has this data. Google Maps has this data, but of course they're not going to share it, right? They don't share. But how can you build this organically from within the city? And not just for Bangalore. If it works in Bangalore, you can do it for 100 other cities within the country. And can you use this for having interventions? So both short-term interventions, such as controlling the traffic signaling across a stretch of the road, based on what the flows across time and across upstream and downstream and so on. But also doing long-term forecasting. What would it take to get 10% of the cars off the street, right? Do I have to introduce a bus line? What's the route I have to introduce it on? What is the effect of having a metro line 10 years down the line, right? In a certain road? Is it going to help with traffic congestion? Is it going to help with livability? Is it going to reduce air pollution? Right? So there are all kinds of questions that we are hoping to answer as part of this project. And this again brings together a bunch of edge analytics, brings in graph analytics, graph neural networks. A lot of the technologies that we worked on IoT and analytics are coming together to help solve this problem. And this is like a 5-year effort that we are just starting now. All right, so that's sort of the motivation from a smart city perspective, using various domain applications. So the last piece of the solution, I would say, right, is the computing layer, right? And here again, there is increasing heterogeneity. There was a time where there's a sense of consolidation, where everything started migrating to the cloud. It was very easy to use, extremely democratized computing, pay as you go, a lot of very good properties, and those still stand, right? So even today, if someone given a choice, I would run things on the cloud because it's easy, right? But even there, you're starting to see fragmentation. One is that you have major players, 3 or 4 major players. You're stuck with them once you adopt them. It's very hard to move away from them. That's one part in terms of diversity. You might also have private clouds that you might have in your university or your organization, which you want to use for sensitive data, when you won't want to put them in public clouds. You also have edge devices, right? And I'll talk a bit more about that, which are complementing the cloud fabric. Even within clouds, with all the concerns about data sovereignty and governance and so on, and Microsoft Azure cloud in UK might have very different policies from one in Ireland across the seas, right? So these are very strict rules and regulations that are being imposed. So it's as much a technology issue as it's a policy issue, right? And these are things that, as sort of scientists or users of the cloud, we have to take into account before we can adopt them in a seamless manner. And edge itself has been rapidly expanding, as many people here might recognize as well, given that there's a big edge AI hub that's being set up across Newcastle and Cardiff and elsewhere. And we have sort of been working actively with some of the more recent accelerated edge devices, right, from Nvidia. These are the Jetson series of devices that you see on the right side. And these have full-fledged, sort of, these are low-end, but full-fledged GPU cores present within, right? In fact, the Orin that I'll show in the next slide has your latest CUDA Ampere cores present within them. So these are again being deployed across smart city deployments, right? So something like this might cost a few $100 or $1,000, and it might be deployed on a street corner as part of deploying 20 cameras. You might throw in a couple of these there as well for doing edge computing. So these are sort of reasonably affordable. These are very compact. Each one of them is smaller than the size of my hand. And these are very energy efficient as well, right? The most energy dense that one of them gets to is about 50 or 60 watts, right? Which is much less than my laptop, right? And some of the ones like the Nano, right? That can be powered off a USB battery pack that you have. So these again are complementing the cloud, and not just for inferencing, which is what they've originally been designed for or pitched by NVIDIA, but also for training, which has been the focus for us in the context of federated learning. And that sort of brings together the full picture, right, in terms of the IoT edge cloud continuum, all the way through sensors and actuation on the left side, to your edge and the fog and the cloud as part of your computing fabric, right? And all of these for doing both data analytics, inferencing, training, and so on. All right, so that sort of brings us to the theme of some of the work that we do in our group, is to see how you can help design software platforms that make it accessible to use these various computing devices, identical computing devices, to build applications that are analytics and data driven and have the nice properties of scalability, resiliency, and so on as well. With that, I'm going to jump into a couple of specific projects, drill down into a bit more detail. But if there are any questions, I'm happy to take them right now, or we can move on to the next topic. Any quick questions?
Have the question at the beginning.
Sure, we'll do that. Thank you. Right. Okay, so first I'll talk about this work that we did in terms of characterizing the accelerated edge device, because the Nvidia Jetsons are, again, relatively new and not many have used them actively for training. In fact, some of the earliest papers that came out in using these platforms for training were from our group. And this is one of the first papers that appeared in Sigmetrics, where we wanted to understand what are some of the opportunities and challenges of using these devices for training. So, and this gives you the trend of how these broadly the edge accelerators have evolved. These predominantly from NVIDIA, but they're also from Intel. They have the Movidius platform. You got Google's Coral and so on. Right? But those are much more smaller in form factor and can only be used for inference, right? When the NVIDIA ones can be used for training as well. And what you see is that while their performance has been increasing exponentially. So the left plot is in log scale. So the fact that you see a linear trend means that you have an exponential growth in the computing power. On the right side, you see that the power drawn by them is linear, right? So the linear growth in power that tops out at around 50 watts, you're getting an exponential growth in the computing power, right? And that's what is a big opportunity over here in terms of doing training on it, right? And this gives you some stats on some of these devices. And we have been predominantly looking at the Orange, which is the most recent generation one, though the profiling study I'll talk about covers the other platforms as well. But the latest generation one has about 2000 CUDA cores of the latest generation Ampere architecture. It's got 32 GB of memory, but this memory is shared between CPU and GPU, right? And 32 GB of memory in a GPU is a lot of memory, right? You don't get that in your workstation grade GPU. So you only get this on the server grade. And you also have ARM based CPU cores. And you have a variety of different storage media as well that you can plug into them, that you can play around with. So the question is, what are some of the opportunities and challenges of these edge devices, which we attempted to profile? And this is your classic ML training pipeline that you might recognize from any of your training frameworks like PyTorch and TensorFlow and so on. You have data that's fetched from disk into memory in mini batches. They are pre-processed in using your CPU. Each mini batch is pre-processed from their native format into tensors that can then be trained, and you launch kernels on your GPU for doing your forward and backward passes, and you get sort of the results back to your CPU. Right? So this is your classic pipeline, and each of these can be a bottleneck when you're looking at an edge device. If you look at a workstation or a server, you're going to see that GPU is oftentimes going to be the bottleneck, right? And as long as you have buy a faster GPU, you're going to be doing okay, but not so on an edge accelerator. Right? So we looked at various aspects of the edge device, everything from how do you tune your software framework? In this case, we were using PyTorch, and how do you select the right storage media, to how can you vary the power mode? And that's one of the power modes are a key control knob in your edge accelerator, which is distinct from what you might traditionally find in your workstations or servers. While workstations and servers, you do have a few CPU frequencies and you have DVFS that you can turn on and so on. These Jetson devices give you 4 major control knobs: CPU frequency, memory frequency, GPU frequency, and the number of CPU cores that are active, right? And together, these come to about 30,000 combinations, right? And these can help give you a trade-off between the compute performance that you get and the energy that you, or the power that you, power load that is available. Right? But how you tune this has a key impact, right? Just because you bump up the CPU without changing the GPU does not mean you'll get better performance in your training, right? So how do you tune this carefully so that you hit a sweet spot when it comes to training, while also minimizing energy is one of the subsequent studies that we've looked into. But before that, just to sort of give you some quick results from this characterization study, we looked at three generations of devices, multiple storage media, using PyTorch for multiple vision models, ResNet, MobileNet, and Linux. So this gives you results on the choice of storage media. The S indicates SSD, D is hard disk, so H is hard disk, and one of them is SSD, one of them is SD card, and the third is hard disk. Right? And what you see over here is that with MobileNet, increasing, going from your SD card, which is your fastest, to the hard disk, which is the slowest, right? That actually causes you to increase the end-to-end training time, which is expected, right? You'll say that, hey, slowed media is going to be a deficit in performance, your IOs being your bottleneck, though your compute is able to keep up, right? But now if you look at a different, so here, this didn't have any caching enabled, and it had number of workers. This is the default setting is for having a single worker that does both IO prefetching, preprocessing, as well as your GPU kernel launches. But by playing around with the caching and as well as the number of workers, right, by having more workers, what you're able to do is that you can actually hide these IO stalls, right, by increasing the number of threads that you allocate for this, right? So that by the time you are done with your GPU training, you've had enough workers pull in data from your disk, do the pre-processing, and have it available to you. And with sort of this page caching enabled, you are able to even hide all the data, like cache all the data, and not even have it visible. So these are these kinds of tunings that you can do to mitigate the effect of, let's say, even a different or a cheaper hard disk storage media. And the other one is, and this can, when you're doing a deployment, if you're deploying 100 of these devices or 1,000 of these devices in the field, going between, let's say, a $50 SSD or a $10 hard disk, right, might have a big impact in terms of the cost of deployment, right? So that's one thing to keep in mind. Another one is sort of the page cache. So with caching enabled for smaller models, you are actually able to reduce the amount of time dramatically, because in this case with MobileNet on the AGX, since you have 32 GB of memory, it's actually able to cache all the training data in memory, right? So this is the 0th epoch. This is the first time that you're seeing the data, doing a full scan for the data. You actually see the hit on the loading time from disk, right? By the time you go to the second round and the third round and so on, all the data has already been cached in memory, right? And that means that you don't have to go to disk, right? When you actually go and build your next mini batch, you're actually just going to in-memory cache, page cache, and loading data from there, and it dramatically drops the training time that you have. So if you're doing a multi-round training till convergence for federated learning and so on, this is going to have a big impact. This again tells you that depending on the data and the model that you're training, even configuring the amount of memory available to your device can have a big impact on the training. But again, that's not seen for devices with lower memory like NX, or for models with a much larger data set, which doesn't fit in memory, like you see for some of the others. And lastly, I'll just show you some results on the power modes. In this case, we picked 10 out of the 30,000 power modes to show the impact of that. Again, with each of these different power modes, you see a different mix in the end-to-end time that you have, as well as for the different models. And this also has an impact on the energy that's consumed as part of this. So this is sort of a Pareto plot that shows the energy consumed on the x-axis and the time taken on the y-axis for these 10 different power modes and 3 different DNN training models. As you can see, there's a bit of a trend, which is sort of expected, whereas the energy consumption increases, the time taken decreases. But that's not always the case. It's not just a linear trend. That's where the opportunity comes in for finding out the sweet spot power mode that gets you the best performance to time, so performance to energy consumption ratio. And so one of the current works that we're doing is, can you actually be much more, can you come up with even better predictions for some of these, just rather than just observations on how they behave, right? So one of the questions that we're trying to answer right now is, can you pick the power mode such that if you have a power constraint, right, can you sort of ensure that your training doesn't cause the power constraint to be exceeded, right, while still minimizing the time taken for training? That's one way to look at it. The other way to look at it is that if you've got a time constraint, saying that I have to finish training by a certain deadline, can you sort of tune the power so that you don't exceed anything more than the required power, right? Can you minimize the power taken, but still try to meet the training, right? And you'd wonder, like, why does it matter, right? 50 watts is not a lot of power. Meaning, why I can just pull it on full throttle, maximum power, and be done with that, right? And in fact, the default setting is to run it at full max N power mode, as they call it. But if you're having these devices out in the field, you might have a constraint on where the power is being supplied. It might not be coming from your mainline power, it might be coming from a battery pack, or it might be coming from solar panel, and so on, right? So there you might actually have a power budget that you have to fall within. If not, you're actually going to be, the system is going to be dead by the end of the day, and it will not be usable at all, right? That's one part. The other part we've recognized is that if you have it in the field, and unlike here, which is a cloudy and cool day for the most of the year, if you have it in India, or if you have it in some sort of rigorous field conditions, it can get very hot, right? And these are all IP67 packaged and so on. So if you go beyond a certain power load, you can actually overheat the system. You can melt the system, right? So depending on how hot it is, right, outdoors, you would actually have a power budget that changes on a daily basis or on an hourly basis, right? So these are two sort of reasons why power ends up being a key constraint. And here we've looked at certain, essentially using ML for systems tuning. We've been looking at retraining these models using transfer learning for making power usage prediction and time prediction for training DNNs. So, and these have been very sort of fairly, it's not necessarily a deep model, it's actually just a shallow neural network models that we've developed. And we've given it a lot of profiling data, potentially several thousand of the 30,000 odd power modes that you have. We sort of profile these and sort of train these neural network models for individual DNN architectures, and try to predict how long they will take under a certain power mode and how much power they're going to consume, right? But this is great if you're always going to be running the same DNN model, right, on maybe new data for continuous learning, and you can sort of do a one-time profiling and be done with it. But what happens if you have different DNN models that are going to be submitted, right, over a period of time? You can't afford to do such profiling studies for thousands of power modes every time, right? So that's where this transfer learning approach comes in really handy, where you build one model, right, based on a lot of profiling data for one DNN architecture, right? And then when a new DNN architecture is submitted for you to do a training, you actually do profiling for on the order of tens, maybe 100 different power modes, right? And then transfer, right, use that for retraining your original neural network model for power and time prediction. And you can, using that, you can actually solve this optimization problem of meeting a certain power constraint while minimizing your training time. Right? So we have some early results on this. Is currently being reviewed as we speak. So here what we see is that in the top right plot, you'll see that NVIDIA itself gives certain tools for doing time and power estimation, right? There is an online tool that you can use, right? And what you see on the left side is how much its its predictions are off, and it causes you to use excess power as a consequence of that. It's actually violating your power threshold, and that's happening more for NV. The blue lines that you see, it's happening more frequently, except for the first one. Everything else, NV is actually doing worse in violating your power limit. While powertrain is our work, and that's sort of falling within, except for the first one where you're actually slightly overestimating. For the rest of time, you are within about 10% or so of your threshold power that you have set. And on the flip side, if you look at the, and if you look, before that, if you look at the actual percentage errors for different power modes on the bottom left plot, you'll see that we are anywhere from around 5 to 10% error for power predictions for arbitrary power mode that you see over here, right? And then on the bottom right, you'll actually see how far there's a time penalty, right? So how much are we off in the estimate, such if you have a suboptimal. So we sort of do a lot of profiling to get the optimal solution. That's a ground truth one, but we don't reveal all of that to this training. But when you sort of use powertrain for doing the prediction, we are actually getting to within barely a few percentage points of your optimal time, right? Compared to the others where they're fairly off, like the neural network, like the random one or the maxen, right? Maxen gives you the most performance, but you're going to have a really bad power usage over there. So all of this in the context of edge accelerators is about optimizing your edge device for doing efficient and effective learning, right? So, so the next part I'll talk about, maybe I have about 10 minutes, is how do you put this to use as part of a larger federated learning framework, right? So earlier work looks at individual edge devices, but now you're going across a cluster of these edge accelerators. So this is a framework, Flotilla, that we've been working on for the past 9 months or so, in terms of coming up with a framework, a very flexible and reliable framework for performing federated learning. For those who are new to federated learning, the idea is fairly simple, right? So Google was one of the early proponents of this, and the use case for them was Google collects a lot of data from their Android phones, among other resources, and they draw a lot of flag because all this data gets sent centrally to the cloud for training various models, right? On which they can sort of do inferencing and they can sort of do better services and so on. And one classic example of this is your Google keyboard, right? The Gboard, right? So there you might have this auto prediction of completions and phrase completions and word completions and so on. And that effectively, every time you actually choose an autocomplete or you don't choose an autocomplete, you're giving a piece of training data to Google, right? Saying that, okay, this person will complete the word in this way. So that's a piece of training data, right? So the next word prediction. So now if the goal over there was to not send this data centrally, right? But still be able to build predictive models collaboratively across millions of users in the world, right? So the idea over there is to keep the data local within each user and train a local model on the local data. Right? So each of these clients will do that independently, and they'll all start with the same randomly initialized global model, G0 over there. So G0 gets shipped to all the edge devices. All the edge devices train on their local training data to get you L1 through LN. That's the first round of training for all the local devices. So all these L1s through LNs, the local models, will be sent centrally, right? And the expectation is that these local models are not as revealing of the raw data as the raw data itself, right? Again, there have been some studies to show that you can get a flavor of the original training data revealed through various kinds of attacks on the trained local model, but at least you don't get the raw data back, right? That's sort of one level of protection or privacy that you get. And within this cloud, you aggregate all these local models, which is extremely simple. You essentially take each layer of your neural network and average the weights to get a global model G1. Right? It's very simple. Right? This is your classic, what's called federated averaging learning model. Right? And then you get a new global model G1. Right? Now you take this G1 and you push it back to all the clients. Right? And now these clients will use G1 as a starting point. Again, train a new local model for the next round of training. And then you'll send this local model back, and you'll do this over multiple rounds until you've converged and stabilized to a certain number of certain global model, which can then be deployed across all the devices for the next version of your Google keyboard or next version of your inferencing model can be deployed on the edge devices. Right? So all of this is a very, very active area of research, federated learning in the last few years. And one of the key benefits of that, obviously, is that you're preserving privacy or you're enhancing privacy by not sharing your local data. Okay, that's one part of it. The other part of it is that in network constrained environments, you're avoiding potentially sending a lot of local data. Right? If your local data is large and much larger than your trained local model, then you're actually conserving network bandwidth. That's the second part. And the third part is that you're also opportunistically using your edge computing, right? If you have it available, rather than doing it centrally in the cloud, right? Because Google obviously will want to reduce their own cloud monetary costs by having you train on your Android phone, which you have purchased, the local model. You're actually reducing Google's cloud computing costs as well. But this is true even for you've got an edge accelerator already on the field, might as well use that for this kind of a trade. So now this is all well and good from a conceptual perspective, right? And it's being put to use in various domains, right? So obviously smart cities is a great example. I talked about the energy prediction in power utilities as one from a privacy perspective. Doing such training on video data out in the field can reduce your network bandwidth and make use of edge accelerators that are present. And from sensitive domains like healthcare and fintech and so on, there, even though compute is not a constraint, it's more about not being allowed to share data due to regulatory reasons, right? Where you might want to, let's say, collaboratively train some kind of classification model, right? So for detecting some signatures in radiography or EEG or so on. So using field devices, right? Can you do that collaboratively across different device manufacturers, medical device manufacturers, right? Is one thing. You could also have things like credit scoring by banks or insurance companies and so on. Without sharing data about the individual, can you actually build a credit risk or an insurance risk model across banks? These are all various use cases for federated learning. Some of these make use of edge devices. Some of these are on sort of full-fledged data centers, but still the principle of federated learning still stands. One challenge that we had noticed, right? So because we've been playing around with this space for the last 2 or 3 years, and one thing that we recurrently, and we've been looking at it more from the systems perspective, right? Because at the end of the day, we are a systems research group. So we want to see how platforms can be enhanced and optimized and so on. It's less so on how we can do ML, how we can do better ML, right? It's not about coming up with a better ML architecture. It's about how can you make the existing ML architecture faster, scalable, and so on. That's what we focus. And what we found is that a lot of the open source federated learning frameworks out there just are not cutting it for us in terms of being able to quickly design, let's say a new FL architecture comes out. We want to design that in one of these existing systems like Flower or OpenFL or FedML and so on, which have been around for at least 4 or 5 years. It takes a lot of these systems are not designed to be modular, right? You can't quickly implement a new algorithm on top of that, right? That's one part of it. And the other part of it is that they don't give you as much telemetry and visibility into what's going on under the hood for you to be able to come and do some systems optimization. So, which meant after a lot of thought, and we essentially sort of pulled the trigger and design our own framework called Flotilla, which tries to look at the federated learning setup from the systems perspective, right? Which means we want it to be modular. You want, and modularity comes in 2 key parts. So one, can you do client selection, right? Because when you're doing federated learning and you got maybe 1,000 or 1 million edge devices to choose from with data on them, you don't always go to all 1,000 of them, right? Because a lot of them might have similar data distributions. So training the same local model on 2 devices having the same distribution is not going to add more value, right? So you want to go to devices with complementary data, right? So client selection becomes very important from a federated learning research perspective. Likewise, aggregation. How do you aggregate data across different local models? Federated averaging is the simplest one, but there are more complex ones as well. That's there. And you also have a lot of strategies with respect to, can you do asynchronous versus synchronous strategies for aggregation? How do you deal with failures? How can you, so the other key limitation for many systems is that these are designed for ML researchers or FedML researchers to simulate on a single device, as if you got a few hundred, right? And which is great if you want to see, does your model converge? But it's useless if you want to actually deploy it on the field, right? Because these are not designed to be deployed. So these are many of them are actually simulation driven alone. So we wanted actually the ability to deploy them on devices as low end as a Raspberry Pi and still be able to work across a wide area network in a distributed setup and so on. So these are some of the properties that we consciously built into Flotilla and addresses some of the limitations of these existing systems. So modularity, sort of ability to scale. We have scaled it so far up to about 400 or 500 devices. We're trying to hit 1,000 in the next month or so for an upcoming paper. Be lightweight, be resilient to failures. Edge devices could fail, network could fail, and you sort of recover from that and move on, right? And have various forms of client selection and aggregation strategies are some of the key goals for this. So you have a server that runs centrally. You got the client running on edge devices. These are designed to be very lightweight. In fact, the client takes barely over 300 or 400 MB of footprint, and a bulk of that actually goes for the PyTorch framework. Our framework itself probably takes only about tens of MB of usage. And the client is extremely lightweight. All it does is does a local model training and does a little bit of coordination with the central server. The central server has more of the intelligence and so on for interacting with all the clients doing aggregation and such. So this is sort of your classic life cycle. The clients come online, they advertise themselves to the central server saying that, hey, I'm available for training. The user deploys sort of a particular federated learning session for training. They submit the architecture along with various configurations of the client selection or the aggregation strategy that they want to use. So then the server goes ahead, does client selection, triggers local training, gets the results back, uses the user-defined model aggregation, and checks if you've reached some convergence. If not, you repeat the whole thing again till you have run enough rounds to convergence. So this is how the big picture architecture looks like. And the advertisement takes place through MQTT, which is very popular for IoT deployments. We have the ability to actually deploy models. The clients can start off with just a clean slate, just having a thin daemon running for Flotilla, as well as their local data that's already there. Right? So that's really the start. And PyTorch framework installed. Everything else happens on the fly. Right? The models get pushed. The client selection happens. The training is triggered. You get the local model. You do synchronous or asynchronous aggregation, and then you do validation. And if it's not converged, you repeat that. So one of the key sort of benefits, just to sort of re-emphasize, is the ability to bring in your own client selection algorithm and your own aggregation algorithm, because these are the two key pieces they have access to. And we've also designed it in such that because these strategies get arbitrarily complex, right? And that itself is how useful are these itself is debatable. I have some slides on that as well. But they need access to all kinds of information, right? So you might need access to how well was the accuracy on a particular client, the last round of training, right? How fast did it happen, right? What is potentially the data distribution of the data on the client, right? So there are very sophisticated algorithms. So what we maintain is a set of states about the devices, about the training itself that's taking place, about the data, and so on. And these are all passed to these algorithms so that they have access to a large pool of state information, which they can then use for designing their algorithms and come up with potentially the next set of clients to use or how the aggregation itself takes place. This gives a lot of flexibility to the developer for coming with new algorithms. To the extent that we were able to design 5 state-of-the-art federated learning papers, everything from things like HPDC and SC and so on, within maybe 3 to 4 weeks, we could implement, right? Maybe even less than that. We could implement all of these and get it up and running. Right? And these are fairly complex algorithms, right? That we got up and running. The other thing that we also have first-class support for is supporting failures both on the client side as well as on the server side. So though you're running in the cloud, it is possible that your VM or your container fails. Right? So we essentially ensure that all the state required for the client are kept in separate dictionaries. These should actually pass to the aggregation and the client selection modules, but they're also externalized and persisted, let's say, on a key value store like Redis and so on, outside the server running your, or the VM running your Flotilla service. So that way, even if the server goes down, you can restart the stateless server on a different device, and you can reinitialize the previous training session and resume from where you left. So we've done some extensive experiments on these on different device clusters, everything from a 40 node Raspberry Pi cluster, having 3 generations of Raspberry Pis, to the Jetson clusters, about 25 node Jetson cluster that we have using, again, multiple generations of Jetson devices, right? So, and we've tried 5 different models, lightweight models like Leonard, time series models like LSTM, which we've used for demand forecasting in Power Grids, to more vision-based models as well, right? And just quick results. So these are all the 5 different strategies that I talked about: Fed average, the classic one, the hacks, Fed async, Fed AT, and I think there's 1 or 2 more that's not listed. And you can see that bottom line, sort of, we are able to closely reproduce, right, what they had in their paper. But it took a lot of work, right? Not because Flotilla was difficult, but most of these papers don't report the hyperparameters, right? So it's literally like dark magic, right, that you have to do, trying out all kinds of parameters till you can reproduce the results somewhat closely, right? And so that becomes reproducibility is a big challenge in the ML space. Right? Other thing we also sort of notice is that, though I don't have a slide on that, many of these frameworks, though they compare against Fed average and they report some results against Fed average that look very favorable, in reality, right, we don't see a big difference from Fed average, right? So, in fact, depending on where you chop off the plot at which round, you can make any case. You can say I'm better than them or I'm worse than them and so on. So, and oftentimes the errors are anywhere between 90 to 95. Doesn't make a big difference. That itself is a question that you have to ask in terms of the additional complexity of this. And these are some plots in terms of how we are able to do resilient recovery. We intentionally kill the clients and the servers, and you're able to sort of converge back to the final result, maybe with a little bit of delay, but without any user intervention. So I'm going to, so with that, maybe I'll wrap up in the next couple of slides. Thanks for the heads up. Now, this is one result on the applying this from practical perspective for the demand predictions in power grids, right? So here we actually used data from the US Energy Information Authority. There's an OpenEIA website where they have data for diverse buildings, both residential and commercial in various states of the United States. And we took Flotilla, right? And we also incorporated some additional characteristics, ML enhancements with some of our ML colleagues on two things. So we did clustering of these various buildings based on how their energy use profiles are similar or different. And for each cluster, we actually built a separate federated learning. Right? So that's one enhancement. The other thing that we also did is, in this case, since we're doing 2 hour ahead forecast, 1 hour ahead forecast of the energy usage at 15-minute time battery. What we also did is that we had to sort of play around with the loss function, right? Because one classic characteristic of time series forecasting, even with things like ARIMA and so on, is that the accuracies of the near horizon is much better. The next 15 minutes, you have a high accuracy. 30 minutes is slightly lesser, 45 minutes even lesser, and so on. Right? So that's why you see a divergent pattern, the most further ahead. So what we did was we actually had an exponential loss function where you penalized errors of further away time points more, right? So that you try to predict further away points much better. And as a consequence, you also end up predicting the nearby points better, right? So you actually, so that kind of exponential loss actually helped us do better. So what you see over here is that using that exponential loss, exponentially weighted loss, EWMSE, you're able to get about 2 or so percentages points better in accuracy compared to just using a classic mean squared error loss function. So that's one thing that we did on top of Flotilla. And the other one is doing clustering. You're again able to get maybe a percentage or 2 better than your default functions, right? Again, so but my comment still stands: is it still really is the others 2 percentages worth it? That's debatable. Depends on the application domain, but it's something that you're able to consistently get as a result. So I'm going to jump past these things. So for those who are interested in functions as a service, we do some work on that on hybrid clouds, on edge and cloud, and so on. For FaaS workflows, there's some cross FaaS work that we do with IBM Research. If you're interested in that, drop me a note. Happy to talk about it. And we also do some work with drone fleets. How can you use those for support visually impaired to have a healthier lifestyle? So here again, there's scheduling aspects and how do you do inferencing on top of these video feeds so that you get a better situation awareness for people who might be visually impaired and a drone is following them. And here we actually operate across edge and cloud as well, using the same kind of Jetson Nano devices that you saw earlier on. And I don't have time for the video, but this will actually show this drone, the Stellar drone, this is off-the-shelf commodity drone, automatically tracking this person as they're walking around, just using the drone, just a nano device, and the individual, right, without any human intervention at all in terms of controlling the drone, right? And then we also do some work with temporal graph analytics for screening graphs and so on, which are used in road networks, but we also put to use as part of COVID in terms of contact tracing for identifying those who are at a higher risk of COVID propagating, right? And there's some recent work we are also doing on federated graph neural networks, right? So federated learning applied to graph neural networks. In fact, we just heard yesterday that it got accepted Europar this year. So that again is combining some of our work on the graph processing with some of our work on federated learning to achieve some benefits over some of the state-of-the-art federated graph neural network learning platforms. Right? So with that, I'm going to stop, and a big thank you to all my students in my group. They do all the hard work. I'll come out and give talks. And thank you all for your patience. Yeah.